Yeah, valence bond theory. This theory was developed in 1931 by Linnaeus Pauling. So this was the third theory given by for the coordination compounds. It was given by Linnaeus Pauling. The central metal atom provides number. What the postulate tells is the first postulate. Before explaining you, here Linnaeus Pauling in 1931 he has explained the metal is the metal atom is considered to be in the ground state. It is considered to be in the ground state electronic configuration. Okay, so that is nothing but ground state of the atom. And as per the valency requirement, metal loses electrons and forms the ionic state. This is the ground state ion. Once again, I'm repeating, metal atom is considered to be in the ground state electronic configuration. That is the ground state of the atom. Now, as per the valency requirement of the metal atom, it loses electrons and forms ionic state. This ionic state is nothing but ground state of the ion. Now, we'll see the central metal atom provides, you're able to understand the central metal atom in the complex, it provides number of empty orbitals equal to coordination number. So for example, you take a metal, you take a complex ML6. So ML6, L is 6, ligands are 6. So the coordination number is 6. So it provides 6 empty orbitals. How many number of the ligands are there? That is the coordination number. And according to the coordination number, the empty orbitals are provided by the central metal atom. So for example, how many number of ligands are, that many number of empty orbitals will be provided. That is the first postulates. So the central metal atom, it is in the ground state, and after losing, it is a ground state ion. And now the central metal atom, it will provide number of empty orbitals equal to the number of ligands. So in the complex, the basic thing is metal should have empty orbitals. Ligand will give 2 electrons, a pair of electrons to the empty orbital. You know, what is a bond? A bond is nothing but it comprises of 2 electrons. Okay, so between 2 atoms, it is nothing but a bond, it will hold 2 atoms together. So for a bond, it requires 2 electrons. Those 2 electrons will be provided by the ligand. And metal contribution is 0. It will just provide the empty orbital. The ligand will give the 2 electrons. Complete contribution of the electrons is by ligand. Contribution of electrons by the metal is 0. So metal will be having empty orbital. Ligand will be giving the 2 electrons. In the previous session, I've explained you. It is denoted by arrow mark. So ligand to metal, there is an arrow mark. Ligand is the donor, metal is the acceptor. So the metal atom, it acts as a Lewis acid and the ligand acts as the Lewis base. So central metal atom provides empty orbitals and the number of empty orbitals is equal to number of ligands. Okay, this is the first point. Now for the coordination with the ligand orbitals. Okay, now the second postulate is empty orbitals. First, here, after explaining these postulates, I'll explain you about the hybridization, so you'll be having a clear-cut idea seeing the examples. So the third postulate, what it was is empty orbitals. Empty orbitals in the metal ion, first of all, they undergo hybridization. Without the ligand coming, before the ligand approaches, the whatever empty orbitals are there, atomic metal empty orbitals will undergo hybridization and they leave over the hybrid orbitals. How many empty orbitals are hybridizing? The same number of hybrid orbitals are formed. For example, two empty orbitals will undergo hybridization. So hybrid orbitals formed are 2. If 3 atomic orbitals, then 3 hybrid orbitals will form. So empty orbitals of metal hybridizes to give same number of hybrid orbitals and same energy will be there almost. So atomic orbital energy, atomic orbitals and metal orbitals energy and the hybrid orbital energy is almost equal and their number is almost same. If two orbitals of metal undergo hybridization, same number of hybrid orbitals are formed. So the same number of hybrid orbitals will be formed. Now the third one is the metal ion will uses n-1 d orbital, ns orbital. So you'll be having s orbital, p orbital, d orbital, f orbitals. You'll be having so many these orbitals. So the metal will be using in this valence, in this complexes, the metal ion will be using the d orbital, it will be using the s orbital, it will be using the p orbital. In the d orbital, you will be having nd as well as n-1d. For example, 4s, 4p, 4d. So here n is 4. So what is n minus 1? 4 minus 1. So here 3d is also there. So what is n minus 1 means? The innermost orbitals. So here the metal ion for its hybridization from its valence shell, it will be using n-1 d orbital, ns orbital, np orbital as well as nd orbital. 4s, 4p, 4d, 4 minus 1 is nothing but 3d, 3d orbital. Okay, so this is the next postulate. Now, the d orbital can be inner as well as outer, what I have explained here. So, metal ion uses s, p, d orbital I have explained. And that d, it can be the inner one and it can be the outer one. If it is n, then you call it as outer. If it is n-1, you call it as inner d orbital. Okay. Now, the next postulate here, the complex with n-1 orbital is inner orbital, and that is the low spin complex. So once in the hybridization, if n-1 d orbital involves in the hybridization, then the formed complex will be low spin complex. Whatever complex is formed, that is a low spin and it is strong field. Low spin and it is strong field complex. Strong field complex. Okay, so n-1 inner orbital, then the low spin is formed and the low spin is nothing but the high field complex. Next postulate, the complex formed using the outer orbital, that is nd orbital, then that is high spin complex. High spin complex. It is nothing but weak field complex. If it is using the outermost orbitals, then you'll be having high spin, but that is a weak field complex. Whatever that complex forms, it is a weak field complex, you can call. Even the non-bonding metal electrons occupy the non-bond. So some of the innermost electrons will not participate in the bonding. The inner d orbitals, so the non-bonding metal electrons, you call them as a non-bonding metal electron. In the innermost shells, most of the electrons will not undergo hybridization and they don't participate in the bonding. Such type is nothing but non-bonding metal electrons. These non-bonding metal electrons do not participate in the bonding. Every ligand, see, since 3 sessions we are saying ligand, ligand, ligand. Ligand can be the negative or else the neutral species, neutral molecule. So ligand is the one which donates a pair of electrons. A complex should form. How it is forming? You'll be having metal, you'll be having them central metal. Previous class I've explained you metal and the ligand. So ligand will be giving electrons to metal, coordinate covalent bond will be formed, and coordinate covalent bond is formed here. So ligand is donating the a pair of electrons, the two electrons, pair of electrons to the central metal atom. So each ligand should definitely have a pair of electrons. So metal is always with the empty orbitals and the ligand should always have the electrons. Then only ligand can act as a Lewis base. It can give two electrons. Then only the metal can accept the electrons. So if the ligand is not having any electrons, how can it give the electrons to the metal? How can the bond form? How can the complex form? So that is not possible. So ligand is nothing but a species, whatever may be the charge, negative or neutral, not the positive charge. Only the metal will be having the positive charge. The ligand will be having negative or the neutral charge, but it should have a lone pair of electrons. Okay, lone pair. What do you mean by lone pair here? Lone pair is nothing but valence shell electrons which are not participating in the bond. So on the head it will be having pair of electrons. They're in the valence shell, but they don't participate in the bonding. They don't participate in the bonding. So they'll be having a free electrons, extra electrons. So thereby this ligand can donate this lone pair of electrons to the metal atom. Thereby it form the coordinate covalent bond. Thereby a complex is formed. So ligand should have lone pair of electrons. Now coming to the third one, a covalent bond is formed by the, it's nothing but coordinate covalent bond, a dative bond. It is formed by, in the complexes, the covalent bond is formed. It's nothing but coordinate covalent bond. It is formed by the overlap of the hybrid metal orbital and filled orbitals of the ligands. As I have told you, a ligand will be having the orbitals and it will be having the lone pair of electrons. These two electrons with this lone pair of electrons in the orbitals will bond with the, will donate these two electrons. The ligand with filled orbitals with the lone pair of electrons will be donated to the hybrid orbital of the metal. Thereby a covalent bond is formed. So covalent bond is formed by the overlap of, see metal, it is already undergoing hybridization, metal atom, ground state, then ionic state, then hybridization. After hybridization, hybrid orbital is formed in the metal. Now the hybrid orbital is ready to bond with the ligand by accepting the two lone pair of electrons of the ligand. So the ligand will donate its lone pair of electrons, its pair of electrons to the metal orbital, hybrid metal orbital. Thereby a coordinate covalent bond is formed. Now, if the complex, now the complex is formed. The metal and the ligand, a complex is formed here. Ligand is donating the pair of electrons to the hybrid orbital, metal orbital, and a coordinate covalent bond is formed and the complex is formed. Now the complex, if it has unpaired electrons, then that is paramagnetic. If it is not having any unpaired electrons, then that is diamagnetic. It is diamagnetic. So under the influence of the strong ligands, strong ligand means pairing of the electrons will take place against to the Hund's rule. What is Hund's rule? First the orbitals get singly filled, then they get doubled. Unless they get singly filled, they don't get doubled. For example, P4 is there. P is having 4 electrons. In that, first 3 electrons will be filled, px1, py1, pz1. Then only the 4th electron will come into the other orbital, into the any of the p orbital. Okay, so first after single filling only, they don't get doubled up before singly filled. That is Hund's rule. So what is Hund's rule? All orbitals singly occupy before they get doubled. All orbitals will singly occupy before they get doubled. That is Hund's rule. But in these complexes, it goes against to the rule, against to the Hund's rule. Here, that is what is the marking. It goes against to the Hund's rule. Under the influence of strong ligands, electrons pair up against to the Hund's rule. Against to Hund's rule. So they don't follow the Hund's rule. Okay. Now let us see the coordination number, the hybridization, and the shapes. What our valence bond theory explains is the structure of the metal complexes, magnetism of the complexes, hybridization of the complexes. Now we'll see the hybridization of the complexes. So once if you see here, the coordination number is 2. What is coordination number? The number of ligands with the central metal atom is nothing but coordination number. If the central metal atom is having 2 ligands, coordination number is 2. So you'll be getting, if hybridization is sp, if hybridization is sp1, 2. So the shape will be linear shape. In case if 3 ligands are there, Ml3, the ligands are 3, coordination number is 3. So the hybridization is sp2. If coordination number is 3, generally you can assume the hybridization as sp2. So the shape will be triangular planar, trigonal planar, trigonal planar structure. If the coordination number is 4, Ml4, M is the central metal atom, L is 4. 4 ligands are there around the ligand. So, see here, the number of hybridization is also coinciding. Here 2, here 2 orbitals. Here 3, 3 orbitals. 2 p's and 1 s. Coming to the coordination number 4, Ml4. So, 4 ligands, 1 s, 3 p. So, the shape will be tetrahedral. Again, sometimes with the coordination number 4, you can get the dsp2 hybridization. dsp2, 1, 2, 3, 4. dsp2 hybridization. The shape can be square planar. If it is 5, the coordination number is 5. The hybridization will be sp3d. Basing on the coordination number, you can explain the you can give out the hybridization. If the ligands are Ml5, so the coordination number, the ligands are 5, the coordination number is 5, and the hybridization will be sp3d. 1, 3 plus 1. So total 5. So the shape can be trigonal bipyramidal. If it is 3, it is trigonal planar. If it is 5, it is trigonal bipyramidal. Next, if it is 6, then you will be having the hybridization 2 times, D2sp3 or sp3d2. This is inner orbital complex involvement. This is the outer orbital complex involvement. So the hybridizations can be 2 types, D2sp3 or sp3d2. But the geometry is the same, octahedral geometry. So basing on the coordination number, you can give the geometry for the complexes. You can explain the hybridizations. So he has explained about the hybridizations. Okay. So these are the postulates. Can I give you a review? Yeah, briefly. So central metal atom will be providing the number of empty orbitals equal to the ligand orbitals. How many ligands are there? So many number of empty orbitals will be provided by the central metal atom. Next, empty orbitals first undergo hybridization. Then only they bond with the ligand electrons. Okay. So the empty orbitals hybridize to give hybrid orbitals with same energy. Next, metal ion uses N-1D, Ns, Np, Nd. If it is N-1, then that is the inner d orbital. And if it is Nd, then that is the outer orbital. Okay. Now, The complex with n minus 1 is the inner orbital. I have told you. It is a low spin complex, and that is a strong field complex. It is a low spin means it's a strong field complex. If the complex is formed using Nd orbital, Nd, if the complex formed using the Nd orbital, that is the outer orbital, that is the outer orbital complex, and it is the outer orbital is being used, and it is the high spin complex. It is the high spin complex and weak field complex. It is a weak field complex. The non-bonding metal electrons occupy. So whatever are there inside innermost electrons, they don't participate in the bond. They are nothing but the non-bonding metal electrons. Each ligand should have lone pair of electrons. Each ligand should have lone pair of electrons. Then only it can bond with the metal. And an arrow mark bond is formed. Coordinate covalent bond is formed. And then only it can act as a Lewis base. And metal can act as a Lewis acid. This donates the electron and the metal accepts the electron. If it doesn't have the lone pair of electrons, it cannot form the coordinate covalent. Next, a covalent bond, how it is getting formed. I told you, ligand lone pair electrons will be donated to the empty orbitals of the hybrid metal orbitals. So a covalent bond is formed by the overlap of the vacant hybrid orbital. So metal has undergone hybridization and the hybrid orbitals are present. Now the hybrid orbitals will bond with the filled orbital electrons of the ligand. Thereby the coordinate covalent bond is formed. If the complex with the unpaired electrons is there, and now the complex is formed, as I've told you from starting of the postulates, I think you can assume how the complex is formed. Now the complex is formed. If the complex is having unpaired electrons, then that is paramagnetic. If the complex is not having unpaired electrons, if it is having paired electrons, then that is diamagnetic complex. Now, under the influence of the strong ligands, Hund's rule is deviated. Under the influence of strong ligands, it is against to the Hund's rule. So electrons. So Hund's rule. What is Hund's rule? All orbitals will singly occupy before they get doubled. Before getting doubling of the electrons, first they should get singly filled. But under the influence of strong fields, strong ligands, Hund's rule is against. So electrons pair up. Okay, against to the Hund's rule. Now hybridizations, we'll see. The Vbt is basically about the hybridizations. So according to the coordination number, metal atom, number of ligands, we can give the hybridization in geometry. So if the coordination number is 2 and the hybridization will be sp and the shape will be linear shape. It will be having the linear shape. So if the coordination number is 3, then the shape hybridization is sp2 trigonal planar. If the coordination number is 4, then that is sp3 hybridization tetrahedral shape. With the coordination number 4, it can be even dsp2, it is square planar. If with the coordination number 5, ml5, then sp3d trigonal bipyramidal. If it is 6, then d2sp3 or sp3d2. It can be octahedral complex. Okay, now we'll see the applications of the valence bond theory for the tetrahedral complex. So we'll see here tetrahedral complex. I have picked up from the academy and I have followed the Agarwal, OP Agarwal Academy. I have referred. So in this, once if you see the Kakatiya series. So here formation of the nickel tetrachloride complex, we'll see. It is an anionic complex. Why? The charge is -2. So this is the anionic complex. Now we'll see tetrahedral complex. So in previous slide I've explained you if it is tetrahedral complex, that will be sp3 hybridization. So nickel ion in the here nickel tetrachloride anionic complex. If you take the central metal atom is nickel and the number of ligands are 4, that the ligands are the chloride here, the chloride ions are the ligands and the nickel is the central metal atom. So here the coordination number is 4. So outside charge of this anionic complex is complex ion. This is a complex ion. It is an anionic complex ion, minus charge. So here it is explained as +2. Previous class I have explained you how to calculate the charge oxidation state for the central metal ion. Once again I am explaining you for this nickel. Nickel you take is as x plus 4 into -1, each one chloride -1 into -1 is equal to -2. So right hand side you put it as -2. So x plus 4 into -1 is equal to -2. So x minus 4 is equal to -2. X is equal to plus 4 minus 2. X is equal to +2. So nickel is +2. Now the electronic configuration of the nickel will see. See, nickel it is 28. It will be having the argon configuration, then 3d8, 4s2, 4p0. So what is the argon configuration? I have a 1s2, 28, you know it is 28. So 1s2, 2s2, 2p6, 3s2, 3p6. Total how many? 18 electrons. Nothing but argon configuration. So previously I have explained here 28. 18 will be there. Argon configuration. 1s2, 2s2, 2p6, 3s2, 3p6. Argon configuration. Then inert gas configuration. After that the valence electrons are 28. So whatever is atomic number, that will be the valency. So 3d8, 4s2. Now this is the innermost orbital. 4s2, ns, np, ns, np. N minus 1 d is involved in the hybridization. N minus 1, 4 minus 1, 3d is involved. So the electronic configuration of the nickel is written here. Now d, you know, d will be having 5 orbitals. Okay, 5. Now yes, only 1. P, you're having 3. Here 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 as per Nernst rule. Now yes, you're having 2 electrons at 2. So here the chloride is the weak ligand, weak field ligand. So they don't get paired up. Okay, understood now? So under the influence of strong ligand, they get paired up. This is a weak ligand, they don't get paired up, these two. They are in the single electrons. So chloride weak field, they are single. So they are not against to the Hund rule. Okay, so 3d8, 4s2, 4p0. Now this is the central metal. Now the charge oxidation state is, I have calculated nickel as +2. +2 is the oxidation state. So the s electrons will be lost here. 2 electrons, +2, 2 electrons lost from the 4s. Okay, after 4s, so 4s is lost. Now 3d8 electrons are there. Now 4p is also there. The valence shell 4p is also empty. Here empty. Now this is the, I have explained, chloride is a weak field ligand. So nickel, it is undergoing sp3 hybridization. Nickel is undergoing sp3 hybridization. So 1 s orbital, nickel atomic orbitals. 1 s orbital and 3 p orbitals. They undergo hybridization, sp3. Here I have told you, sp3 hybridization. So nickel, it is +2 charge now, 2 electrons lost. Okay. Now for this nickel +2 charge ion, This is the configuration. Now, in presence of ligands, the chlorides are coming nearer to the central metal atom. So, this will undergo hybridization before the chloride ions approach nearer this central metal ion. It will undergo hybridization. Its atomic orbitals will undergo hybridization to give hybrid orbitals. Same number and same energy. So, one s orbital and a 3p orbital. So, it is sp3 hybridization. So, how many orbitals? 1, 2, 3, 4. sp3, how many are formed? 4. 4 atomic orbitals combined to give 4 hybrid orbitals. So how many sp3 orbitals are formed? 4 sp3. 4 atomic orbitals combined, undergo sp3 hybridization, and the hybrid orbitals are formed. Each hybrid orbital, you call it as sp3. Such type of sp3 hybrid orbitals are 4. Same number. Okay, so 1s, 3p. Combine, undergo sp3 hybridization, 4 sp3 hybrid orbitals are formed. Now, nickel is in the center. Nickel is in the center. And 4 sp3 hybrid orbitals are in the tetrahedral arrangement with empty, no electrons. And they're empty with no electrons. So, the nickel ion, Ni plus 2 ion, atomic orbitals have undergone hybridization, sp3 hybridization. 4 sp3 hybrid orbitals formed. They're arranged 4 no. So previously I have explained you 4 is the coordination number for chlorides. How many are the ligands? How many are the so many empty orbitals have been provided. According to our postulate, the central metal ion, according to the number of coordination number, nothing but ligand number, this will arrange the empty orbitals. So 4 chloride ions are there. It is showing 4 hybrid orbitals. It has formed 4 hybrid orbitals. Now it is ready to bond with the chloride ligand. So nickel is in the center and 4 sp3 hybrid orbitals of the nickel are in the orientation of tetrahedral arrangement. Okay, 4 directions there. Now the chloride ions have approached the nickel ion. So each chloride ion, 4 chloride ions, weak field chloride ions. So because this is weak field, they are not getting paired up. Okay. So 4 empty orbitals, 4 chloride ions. Each chloride ions will give pair of electrons to empty orbital. Here, one chloride is giving its 2 electrons to the empty sp3 hybrid orbital of the nickel metal atom. Again, another chloride, it is giving its 2 lone pair of electrons to the empty hybrid orbital of the nickel. So in the similar fashion, 4 chloride ions donates 4 pairs of electrons to the 4 hybrid orbitals of the nickel. Thereby, it is forming nickel tetrachloride anionic complex. Here you are having 2 single electrons. Now the complex is formed and the complex is having 2 single electrons. Once if the 2 single electrons are there, then the complex is paramagnetic. It is attracted by the external magnetic field. That is nothing but paramagnetic in nature. So the hybridization is sp3, the complex is tetrahedral and the complex has 2 unpaired electrons and it is paramagnetic in nature. Okay, I hope you have understood this complex. Now let us go one more example of the tetrahedral. Now we'll see the very important complex, a formation of nickel tetracarbonyl complex. This is a neutral complex. Is there any charge over here? No. So it is a neutral charge complex. If it is plus, cationic complex. If it is minus, then that is the anionic complex. If it is 0, no charge, then that is the neutral complex. Nickel tetracarbonyl, capital C, capital. See, cyanide and the carbon monoxide are a very strong ligands. These are the strong ligands. In nickel tetracarbonyl complex, we'll see how the bonding is there. Nickel, it is a 0. Oxidation state. Previous class, I've explained you about the oxidation states. So, the carbon monoxide is the neutral ligand. So, 4 into 0. See, according to oxidation state, the charge is 0, but it will donate electrons. Okay, it is a ligand. It will donate the electrons to the central metal atom. That is secondary. But the charge of the carbon monoxide, this is the neutral ligand. Neutral ligand. Okay, so the charge is 0. So x plus 4 into 0, x plus 4 into 0 is nothing but 0. So x is equal to 0. Therefore, nickel oxidation state is 0. Okay, so now we'll see the bonding. Electronic configuration of the nickel. So nickel, I have told you it is 28 atomic number. 1 here, argon configuration, inert gas configuration. After argon it is 18. Then 3d8, 4s2, 4p0. Argon configuration, you know, no? 1s2, 2s2, 2p6, 3s2, 3p6. That is organic configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, 4s2, 4p0. This is okay. Simply you can write with the inert gas configuration. Argon configuration, then 3d8, 4s2, 4p0. Now, this is the d orbital having 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now, S is having 2 electrons. Now, P is having 0 electrons, empty orbitals. Okay, so N minus 1 d orbital is involved, Ns, Np is involved. Now, carbon monoxide is a strong field. Previously, I have explained you chloride a weak field. Okay, this is a strong field. Like carbon monoxide is a strong ligand. So as the strong ligand is coming, what happens? What happens? So these electrons get paired up here. Okay, these electrons are jumping and they get paired up here. Now 4 empty orbitals are 1, 2, 3, 4. Okay, now these 4 orbitals S, P, 3 orbitals Px, Py, Pz. So 4s orbital, p orbital, px, py, pz. So 4 atomic orbitals, nickel metal atom. So 4 nickel metal atom orbitals undergo hybridization. 4 will combine to give 4 hybrid orbitals. 4 atomic orbitals combine to give 4 hybrid orbitals. What are the atomic orbitals? S, 3 p's. Okay, nickel atom atomic orbitals, 1s orbital, 3p orbitals combine to give 1s and 3p orbitals. So therefore 4 sp3 hybrid orbitals are formed. So nickel is in the center. The atomic orbitals have undergone hybridization. They have undergone the hybridization. sp3 hybrid orbitals are formed. So 4 have combined. So 4 hybrid orbitals formed. They are arranged in a tetrahedral manner. 4 sp3 hybrid orbitals. So nickel is in the center, 4 sp3 orbitals in the tetrahedral arrangement. Now the nickel has undergone hybridization, it's waiting for the nickel. Sorry, nickel is waiting for the carbon monoxide. Ligand. So the carbon monoxide approaches nickel hybrid orbitals. And each carbon monoxide, here it should be capital O. Okay, just like this. Capital C, capital. Okay, capital C, capital. So this will donate a pair of electron to hybrid orbital. Second carbonyl also donates its pair of electrons to second hybrid orbital. In the similar fashion, the 4 carbonyls, carbon monoxides, will donate their pair of electrons to the empty hybrid orbitals of the nickel. So therefore, they undergo bonding with the nickel central metal atom. So nickel tetracarbonyl is formed. nickel tetracarbonyl is formed. So it is sp3 hybridization, tetrahedral geometry will be getting. This complex, is there any lone pair of electrons? Is there any of the single electrons? No. Is there any single electron? No. So all paired up electrons. Everything is getting paired. So it is diamagnetic in nature. Diamagnetic in nature. So strong field I have explained you, and a weak field I have explained. So these are the postulates and the applications of the VBT for tetrahedral complex. I hope everybody have understood. So I have explained about the valence bond theory, their postulates, then hybridizations, and their applications. Application for the weak field I have explained, and I have explained for the strong field. So next class, I'm going to explain you about the square planar complex as well as the octahedral class, octahedral inner orbital complex and outer orbital complex. Thank you, everybody.